Doing a short video here to discuss a couple of conditions that can occur when you're trying to repair a radio. These two are referred to as motorboating and IF transformer self-oscillation. They are annoying things to try and diagnose because you go through the process of trying to repair a radio. You've gone through all of the capacitors, for example, and you've checked them and replaced the ones that are leaky. And then you turn it on for the first time and you hear an awful noise. It's not working, and you try to tweak the IF transformers and it's just not working. So I've got this radio set up. For this case, the condition here is what we call the IF transformer self-oscillation. And what you'll hear here is a very high-pitched noise. And as you tune around a station, you'll hear the pitching change. And you may hear a little bit of the station coming in, but if, for example, you try and tweak the IF transformer to try and tune it in, you may get some motorboating, the pitch will change, and it just won't tune in, no matter what you try to do. This is typically caused by inadequate shielding of either the IF amplifier stage and the converter, or the first IF amplifier stage and the detector. On these older radios with the 12S series tubes, these are metal shielded tubes, and the shields are often connected together, and then they're connected to the chassis with a capacitor to provide an AC coupled ground. Not a DC coupled ground, it's an AC coupled ground, so there you use a capacitor. So if you look closer in here, I've got two capacitors here of note. This one here is actually connected to the shields of the IF gain stage, the first IF gain, and the detector tube. So this has got the dual diodes in there for the demultiplexer, the decoder, and it also has a triode in there for the first stage of amplification of the audio. As you can see here, this capacitor is not connected to anything, it's just floating. I've got this thing on an isolated power supply, so I'm not really in danger of electrocuting myself here, but still you have to do some precautions to make sure that you don't zap yourself. But anyway, I'm just going to short this, and once we get it back,
my opinion, if the RCMP is doing good work, it shouldn't at all be threatened with a layer of oversight.
we can see that we can. I will permanently do this at some point, but you can see that the station actually comes back, and you can now tweak the IF transformers and get it back to working again. Now I'm going to fix this, and I'm going to go on to the next stage of problems, which is the subject of motorboating. And this is the second issue that you can sometimes come across, which is what we refer to as motorboating, which is a peculiar sound that the radio makes under these conditions. So if I turn up the volume a little bit and I touch it, you notice that the radio is beating at a fairly low frequency. And as I tune around the station, it will make different sounds that are referred to as motorboating, in that it kind of like makes a putt-putt sound as it oscillates. And in this particular case, the fault is due to an inadequate coupling between the chassis ground and the circuit ground, which is these two safety capacitors here, which are supposed to be hooked to the chassis ground. On one side, the capacitors are hooked to the circuit ground, and the other side is floating. It should be on chassis ground. So I have this problem occurring. If I connect that back together again,
What do you think of the RCMP's initial response? Because they said, look, investigators,
I get
looked at it,
radio
they
returning back to
determined
normal
that the
and it
actions the
operates
police took
correctly.
were within the continuum of the use of force.
So I'll get back in a minute. We'll clean this up and we'll take a look at the schematic and we'll see where these capacitors are and these checks that should be made. And just before I leave though, I want to sort of point out something here that I made a change to. We'll talk about this in the circuit as well. And that happens to be this particular capacitor here, which is hooked up to circuit ground on one side, and it's hooked up to the RF front end oscillator on the other side. This is a common ground point for both the local IF oscillator and the RF front end tuning coil. If I didn't mention earlier, this is a Crosley style radio, which is a combination of broadcast and shortwave, where the shortwave is from 6 megahertz to 15 megahertz. The shortwave actually does work fairly decently on this radio. It's pretty selective. And this is a Crosley model G2465. I believe it's a circa 1946-ish. It's using the 12S series tube, so that's typically that era of radio. In that the tubes layout used is the older style series with I think it's a 35Z5 and a 50L6 output tube. So let me get this cleaned up and we'll come back and look at the schematic and see where these problem spots are. So I've got a schematic here. Just as an aside, what I did here is I took the original PDF of the schematic that I found and I kind of redrew it out and I checked it against the radio that I had in front of me. I do this for a couple of reasons. Number one, it helps me to sort of better figure out what the circuit is doing. Quite often in the schematic, you don't really get a good idea of what the circuit layout is actually doing in terms of DC and AC current flow, because the diagram's really laid out for the technician and it's really there to sort of show him what's connected to what, and it's less to do with analyzing a circuit and seeing actually how it functions. So that's the reason why I have all of this hand printed out. Plus I can make my own notes on it and I can figure out what the designer was doing, and in some cases I might even make some improvements or changes. So anyway, the first capacitor we looked at, which was the IF self-oscillation, was this capacitor here, C13. As you can see, it's connected to chassis ground on one side, and on the other side it's connected to pin 1 of the 12SQ7 and the 12SK7. So this is the first IF amplifier, and this is the detector and first stage audio amp tube. Disconnecting this means that the shields, the metal cans on those two tubes, are floating. They're not connected to the chassis ground, and then they can pick up all sorts of noise from the environment. In some cases, the tube shield may also be connected to another grid inside the tube, which is something to be aware of. In the case of the 12SA7, which is the converter tube, pin 1 here is actually also connected to one of the grids. But in the case of the motorboating or the IF oscillation, I just floated these two tube shields here to cause the problem to occur. You can also get the same problem if the shield around either IF transformer is inadequately tied to earth. It's not shown in the drawing here, but these cans are actually tied to earth through a mechanical fastening. In this case, it's the hardware that holds the tube onto the chassis. So if I bring the radio in here, you can see here there's the second IF transformer. It's mechanically bolted down to the chassis. That mechanical coupling, see if we can also get a picture of it from underneath. There we go. I could just make out the, if I can see it in the camera. Yes, there it is. There's one there, and then the other one's over here. So these two hardware nuts shield the IF transformer. If that is not adequately done, the shield is floating and the IF transformer can also oscillate. So one potential reason why self-oscillation occurs is that the magnetic field couples into the first IF transformer tube because the shield is floating, and then you have an implicit feedback loop that occurs here, and this thing effectively turns into an oscillator excited by the energy from the station that's coming in. So the beat frequency of a station mixing with the IF can excite the transformer, and that noise is then demodulated and sent out the speaker. So the second capacitor we looked at, which is C21 here, this is the connection between the circuit ground and the chassis ground. Now this is important because it ties chassis ground to a ground. So it's now AC coupled to a reference point, which in the case of this case is the neutral of the AC coming in. On these radios, I change out the plug and I make it the plug is not a one you can plug in both ways. There's one of the tangs is larger on these plugs, so that they're keyed such that you can only plug them in. Let's get that into shot. The plug is polarized, so there's a larger pin and a smaller pin. This pin is hot, and this pin would be neutral, as long as the wiring in the house is done correctly in North America. So this side here is this line here, and this is implicitly tied to chassis, making the chassis itself, the IF cans, and the metal cans surrounding the glass tubes shielded. The third capacitor that I pointed out, which was the one I said to make note of, is this is kind of a side issue, but that was this capacitor here. And I was trying to figure out why this capacitor, which hooks into the common side for the IF coils, the local oscillator coils for the broadcast and shortwave, and also the common side for the antenna loop, was tied to AVC. This made not a lot of sense to me, because why would they tie the common point of the front end through this capacitor to AVC, the voltage control, automatic voltage volume control? The only thing I could figure out is that they were tying it essentially through this capacitor and then through the AVC filter to ground, thus providing an AC ground for this circuit over here. just for fun, I actually disconnected this here, and I actually hooked it up to ground like that, and it works just fine. In fact, it works a little bit better. So it's still a mystery to me why they did it this way. I find that if I just tie this directly to ground, it works just fine. There's no issues with it. So unless I can figure out some real reason why they did it this way, I'll just probably leave it that way. So the third part of this, we'll just take a look at the original schematic, and I'll basically go through what it looks like and show the same capacitors. But I just thought I'd just fire out this quick video and show people some cases where, you know, they've repaired a radio, it's oscillating, and they don't know why, and it's frustrating because you got this thing repaired and it's just not working anymore, and you're thinking to yourself, oh no, I've botched it up, you know, this thing's never going to work again. When all in all, it's just basically just retracing your steps, making sure that all your connections are good, making sure that you didn't make any changes to the circuit in a drastic fashion. For example, moving a coupling capacitor from one location in the circuit to another location that may not work as well. This brings us to the final thing I'd like to say about this, which is what's called lead dressing. The original layout of the radio is quite often very critical in terms of where the wires are going and how they've been what we call dressed. An example of that, which can cause problems, is the connection between the converter tube output, the plate, and the first IF. In the circuit, I'm talking about this connection here. This wire is kept intentionally very short. The physical distance between this here in the IF can and here in the tube is short. The wire is kept separated from the grid, any inputs, to minimize coupling and causing feedback. In the case of this radio here, you can see that the output of the tube, which is pin 3, so 1, 2, 3, this blue wire here, goes directly from the tab on the tube socket directly into the transformer housing. So this wire is kept as short as possible. Grid on this tube is pin 8, which is over here. So it's about as far away from that as it could be. That goes up into the guts of the circuit and off to the switch, the selector switch. So it's nowhere near that. If you were to make this wire close to this wire, or make this wire longer, or loop it around such that it was in closer physical contact with the grid, you can get the same effect, motorboating or howling or IF oscillation, because this is a very high impedance input, and it doesn't take much to inject energy into it from the output, which is a much lower impedance, much more energy in the output. So that's a consideration to take in mind as well. I just brought up the original PDF of the radio here, just as a comparison, showing what I had to work off of to create the schematic, my layout design of the schematic. The circuit design, as you can see here, is very compact. The circuit ground starts here, wraps around, and kind of folds back over the top. A very unconventional way of drawing, but they laid out the circuit to be as small as possible so it could fit on one page. So it was for the benefit of the document, and not so much the benefit of someone who was trying to work out the theory behind how the circuit worked. This is the AVC capacitor, for example, and here's the AC coupling ground capacitor here for the front end. that I had moved over to circuit ground. So the two topics that I discussed today are also in documentation of the day. This is an example of one of those from the National Radio Institute. The subject is how to make extra money fixing radios, which is something that was, a lucrative business back then. This case, it's issue number 23, how to fix a receiver that squeals in motorboats, radio servicing methods. It's actually a very nice, detailed document. I would recommend, picking it up. I just did a Google search for it, and the title of it is how to fix a receiver that squeals in motorboats. It's a PDF. If you just Google for it, you should be able to find it fairly easily. It pretty much goes through the same topics that I talked about in the video. It talks about oscillation, why it occurs, feedback, how capacitive coupling between the plate and the grid can cause feedback to occur. And that refers to the lead dressing that I talked about in terms of the front end being very high impedance and very sensitive to this type of capacitive coupling. It gets on into also the subject of keeping the leads short, separated, as I talked about. Possible other potential issues with capacitive type of feedback. This is probably less of an issue because by the time you've gotten to this point, you've probably gone and tested all the capacitors for leakage and replaced the ones that are leaky, or have just done an all wholesale replacement of all old paper wax capacitors. I'm not going to go through the entire document here. I'm just going to show you what they're covering here. They're talking about shields in terms of tubes. This is in the case where older radios were using glass tubes without external metal shields, and the 12S series in this radio doesn't have that problem because the shield is built into the tube itself. There's actually a glass envelope inside of that metal can. The metal just serves as the RF shielding for the tube. So I hope that the subject of the matter of this video, I hope that the content of it was useful to other people. It can be daunting and frustrating when you come up to a problem where you've replaced all the capacitors in a radio and it just doesn't work. It's worse than before, and it's very disheartening when that occurs. You just have to kind of step back, take a deep breath, take a look at what you've done to the circuit, retrace it. If you need to, go through the schematic and redraw parts of it so it makes more sense to you. Take a look for common problems with maybe a bad solder joint, inadequate grounding or coupling between a shield to chassis or a ground to chassis issue. Take a look at lead dressing. Maybe you've moved some leads around and that's starting to cause feedback. So anyway, I hope everybody's doing okay, and I'm going to leave it off at that, and I will try to make another video up in the near future. I'm toying around with maybe starting a series on a small tube monoblock using 6AQ5 tubes. We'll see how that works out. Anyway, take care.